Good morning, everyone. This is Sachin Piske from Electrical Engineering Department, S&D College of Engineering and Research Center. In the previous lecture, we discussed about the block diagram reduction technique. Now we are start the new topic, Rouths criteria or root stability criteria. Let us consider one closed loop transfer function. As per the definition of transfer function, G of S is equal to C of S upon R of S. And we can consider this G of S is equals to H of S also. So H of S is equals to, in numerator and denominator, these two sides are to be considered. So consider first numerator, that is B0 into S to the power m plus B1 into S to the power m minus 1 plus dot 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 plus B m minus 1 into S plus B to the suffix m upon A0 into S to the power n plus A1 into S to the power n minus 1, means its power of S will be goes on decreasing, and at the same time the coefficient of this S is also goes on decreasing, that is a to the base or 8 suffix n minus 1 into S plus a to the n. Okay, and it is equals to B of S upon A of S. This is equation number 1. Here A1 of S and BI of S and BI of S are the real constant, and the value of M is less than or equal to N. An alternative to factoring the denominator of the polynomial, this root stability criteria determines the number of closed loop poles in the right half plane. See this algorithm for applying the root stability criteria. The algorithm described below, like the stability criteria, requires the order of A of S to be finite. See one by one. The factor out any roots at the origin to obtain the polynomial and multiplied by -1 if necessary to obtain A0 into S to the power n plus A1 into S to the power n minus 1 plus so on plus a n minus 1 into S plus a n is equals to 0, means we have to equate the denominator is equals to 0 to get the pole. This is equation number 2, where this a0 is not equals to 0 and an should be greater than 0. These conditions to be verified. Secondly, if the order of the resulting polynomial is at least 2 and any coefficient, that is ai, is 0 or negative, the polynomial has at least one root with non-negative real part. To obtain the precise number of the roots with non-negative real part, proceed it as follows. Arrange the coefficient of the polynomial and values subsequently calculated from them as shown below. So all these orders means the s to the power n, n minus 1, n minus 2, n minus 3, n minus 4 are considered in first column, and the remaining coefficient just like a0, a1, then b1, c1 and d1, a2, a4 and a6 in a single row, then a1, a3, a5 and a7 in the another row. So b1, b2, b3, b4, then as per the s to the power n minus whatever the value will be considered in a particular row and column arrangement. Then from s to the power n towards s to the power n0 we have to stand it, where the coefficient of bi are b1, b2 and b3 we have to calculate as per a1, a2 minus a0, a3 upon a1, and b2 is equals to a1, a4 minus a0, a5 upon a1, and b3 is equals to A1 A6 minus A0 A7 upon means equation 4, 5 and 6 were obtained from equation number 3 by considering a simple matrix arrangement one by one. We are going to take here we are generated until all the subsequent coefficients are 0. Similarly, cross multiply the coefficient of the two previous rows to obtain the CI of CI, DI and etc. So C1, C2 and C3 and similarly D1 and D2 will be obtained. Just take C1 and D1, that is C1 is equal to B1 A3 minus A1 B2 upon B1 and C2 is equals to A1 F B1 A5 minus A1 B3 upon B1 and C3 is equals to B1 A7 minus A1 B4 upon B1. Just similarly, we get D1 and D2 as C1 B2 minus B1 C2 upon C1 and D2 is equal to C1 B3 minus B1 C3 upon C1. So equation 7, 8, 9, 10 and 11 just are obtained by the matrix cross multiplication. Here, until the nth row of the array has been completed, missing coefficients are replaced all by 0 and resulting array is called the Rouths array. The power of s are not considered to be the part of the array. Now we can think of them as labels. The column being with A0 is considered to be the first column of this array system. This is the main fundamentals of this Rouths criteria. Now, this Rouths array is seen to be a triangular. It can be shown that multiplying a row by a positive number of a simplify the calculation of the next row does not affect the outcome of the application of the Rouths criteria. And now, count the number of the sign changes in the first column of the array. It can be shown that a necessary and sufficient conditions for all the roots of 2 can be located in the left half plane is that all AI are positive and all the coefficient in the first column should always be positive. One more thing is that whenever we are going to arrange this matrix, it should be noted that the value of s or coefficient of this s should be from n to 0, means we should have to arrange from maximum value to minimum value, and it should be kept in the mind that the first value should be always be equals to 1, means coefficient of a0 should be 1. Similarly, at the second term a1 should be 1, means while whenever we are going to calculate all these values should equals to 1, so that the poles of the particular system we can easily obtain. So each and every equation can be obtained by placing a simple matrix, and whenever we are going to place a matrix we should easily get the value of b1 b2 b3, similarly the value of c1 c2 c3 and the value of d1 and d3. These Rouths criteria are basically used for the simplicity of a particular matrix. Generally, in control system engineering, we provide this Rouths criteria as equivalent to this system, as equivalent to the Nyquist plot arrangement. But as per this Nyquist plot, this system is outdated, and we are generally use Nyquist or Bode plot system to get the simple solution of a control system. Thank you.